The night sky carries a hidden melody, a precise harmony that guides the orbital dance of planets, moons, and comets. The music of the spheres reveals how that idea links mathematics, astronomy, and music across centuries. We trace the arc from Pythagoras to modern physics, showing why ratios and resonances still shape how we listen to the cosmos. Through visuals, demos, and real-world examples, you'll see why this ancient concept remains surprisingly relevant today. Stay with us to hear the universe's soundtrack laid bare and discover what that sound can tell us about our place among the stars. Origins and historical context. The idea that celestial motions embody a harmony predates modern science and emerged from a synthesis of mathematics, philosophy, and observation. In ancient Greece, numbers and ratios mattered beyond arithmetic. Pythagoras and his circle linked the ratios governing vibrating strings to the order they observed in the heavens, proposing that the universe was organized by proportion. Sound and sky were treated as connected. The heavens were imagined as a system of transparent, concentric spheres whose movement produced an invisible music that sailors and scholars could sense as order. Even if no note rang aloud, the metaphor held power. In the medieval world, the notion traveled through translation networks and scholastic schools, taking on structure and doctrine. Musica universalis became a framework. Thinkers tied planetary motion to musical intervals, and the cosmos to a grand tuning fork that humans could never hear, yet could imagine as perfect symmetry. Cathedrals themselves were read as acoustic maps of proportion. Dante, in his cosmological map, and other writers used harmonic order to frame moral and spiritual ascent, casting the heavens as a chorus that mirrors human pursuits of virtue. The literature echoed with ratio and resonance. With the Renaissance and the uneasy shift toward new astronomical ideas, the music of the spheres persisted as a poetic and heuristic guide, even as empirical inquiry began to reveal more complex mechanics. Kepler stands as a bridge between belief and measurement. He argued that celestial relationships could be understood through harmonious correspondences, a stance that elevated music theory into a way of thinking about nature's order. The model did not stop being music to artists and astronomers. Instead of implying audible tones, it suggested a program. Look for harmony in ratios, proportions, and geometric forms, and let those patterns illuminate the architecture of the cosmos. In modern times, the phrase survives as a powerful metaphor that informs art, literature, and speculative science, inviting audiences to sense coherence in vast, dynamic systems. Music continues to echo the idea. Composers and writers invoke the antique slogan to frame space as a grand instrument, while scientists use the concept as a reminder that natural laws tend to reveal themselves through relationships and symmetry. Gustav Holst's planets and various space-themed works show how the ancient dream still resonates. Even when specific celestial mechanics are understood differently, the dream of a harmonized cosmos endures as a narrative technique that helps people grasp scale, order, and beauty. Mathematical foundations of cosmic harmony. Cosmic harmony emerges from the mathematics that describe how bodies move under gravity. The core is a Hamiltonian framework where energy and angular momentum are conserved in the ideal two-body case, producing elegant, closed orbits. When more bodies are present, small perturbations break perfect closure but still carry a rhythm that can be parsed with careful approximations. Mean motion resonances appear when orbital frequencies are near simple ratios, such as 2 to 1 or 3 to 2, creating a cadence that can lock together the motions of bodies. In this picture, orbits sway between libration and circulation, tracing patterns that resemble musical phrases rather than random chaos. Fourier analysis translates orbital motion into a spectrum of frequencies, much like turning a melody into notes. Any periodic or quasi-periodic component contributes harmonics at integer multiples of a fundamental frequency, and combinations of frequencies produce sidebands that enrich the tonal texture. For a planet in a near-circular orbit perturbed by distant planets, the spectrum typically features a strong fundamental corresponding to the mean motion and a handful of harmonics and combination frequencies. This spectral fingerprint encodes stability. Dominant, clean peaks point to regular motion, while broad, crowded spectra signal more complex, potentially chaotic evolution. Beyond point masses, the shape of bodies matters. The gravitational potential can be expanded in spherical harmonics, with the monopole term setting the central pole and the quadrupole and higher terms shaping precession of orbits. The leading non-spherical contribution, the quadrupole, gives a steady drift of orbital elements such as the argument of periapsis and the node, effectively weaving another layer into the cosmic soundtrack. In planetary systems, such terms influence long-term coherence and can either reinforce resonance patterns or slowly erode them, depending on the geometry and mass distribution. Practical tools for exploring these foundations include numerical integrators that preserve the Hamiltonian structure, like symplectic schemes, which keep energy drift minimal over long runs. Frequency map analysis and other spectral diagnostics help separate regular from chaotic sectors of phase space and reveal the resilience of resonant chains. In exoplanet and moon systems, engineers and scientists rely on these techniques to assess stability criteria, forecast possible resonance locking, and interpret observed orbital configurations as echoes of a shared mathematical rhythm. The mathematics of cosmic harmony is thus not distant poetry, but a toolkit that translates motion into a language of spectra, modes, and stable patterns we can measure and test. Historical pioneers, from Pythagoras to Kepler. The idea that celestial motion carries a musical resonance emerged in ancient Greece when thinkers connected numeric harmony with the order of the heavens. Pythagoras is credited with discovering that simple vibrating strings give notes in neat whole number ratios. The octave is 2 to 1, the fifth 3 to 2, and the fourth 4 to 3, and these ratios provide the ear with a sense of consonance that many linked to cosmic order. From these observations grew the belief that the heavens themselves obey a kind of music. As centuries passed, the idea matured into a broader framework called musica universalis, a philosophical claim that the cosmic motions harmonize like a vast orchestra. Medieval and Renaissance thinkers linked planetary motion to the rhythm of the spheres, treating the heavens as if they sang in tune. Pythagorean principles persisted in musical theory and in the architecture of scales, shaping how people heard order and beauty. Johannes Kepler took up the thread and pushed it from metaphor toward measurable structure. In Harmonics Mundi, he proposed that the distances and orbital relationships of the planets could be expressed as musical intervals, a bold attempt to quantify cosmic harmony. Alongside this, his laws of planetary motion gave a precise mathematical description of how celestial bodies move. The practical thread from Pythagoras to Kepler fed developments in tuning and timekeeping, where the aim was to capture consonants in instruments and voices. Pythagorean tuning favored pure fifths, yielding a bright, ringing balance but facing challenges when expanding beyond a single key. Kepler's fusion of music and astronomy reinforced the idea that numerical relationships govern both sound and motion. This cross-pollination left a durable cultural footprint, coloring how people imagined order in nature. Today, the phrase lives on as both a poetic metaphor and a method, as scientists and artists translate celestial data into sound to explore patterns. The enduring impulse is to listen for structure amid complexity, whether in a keyboard tuned to pure intervals or in a sonified dataset that reveals hidden connections. The music of the spheres remains a bridge between mathematics, perception, and imagination. Contemporary interpretations, physics, music, and visualization. The idea that celestial motions carry a kind of harmony persists in modern science and art. In physics, gravitational dynamics produce regularities that can be described with mathematics, and those regularities can be rendered as music or visualization. Contemporary practitioners use sonification to turn measurements of orbits, resonances, and space plasmas into audible patterns. Artists and scientists collaborate to create installations where the rhythm of a planetary system drives live sound and visuals. Orbital dynamics organize motion into resonant structures that scientists model with precise simulations and equations. When bodies exchange energy through resonance, predictable cadences emerge, which can be heard as recurring motifs in a composition. The gravitational field acts as a conductor, guiding the tempo of orbital motion, while differences in mass and distance shift the harmony. Visualization and analysis tools reveal where order gives way to chaos, and where a slight change can alter the cadence. Sound is not a literal recording of space, but a translation of data into tones, rhythms, and timbres. Maps of orbital periods, precession, and velocity vectors can be encoded as scales, arpeggios, or percussive motives, letting listeners perceive dynamics that are invisible to the eye alone. The same data that describe a stable resonance can be sonified as a gentle drone that subtly shifts as a planet's orbit adjusts. In another strand, gravitational wave signals are often rendered as audible chirps, giving tangible access to the cosmos's most violent events. Visualization platforms fuse motion and sound into immersive experiences. Tools like Universe Sandbox let users adjust masses, angles, and speeds and watch how trails morph and resonate, which makes abstract concepts tangible. Educational and artistic projects pair data-derived music with three-dimensional diagrams, color-coded by velocity or energy, to communicate how harmony arises from gravity. Exoplanet systems are often presented through sonified or color-coded visualizations to illustrate resonances and orbital stability. The contemporary approach shows that the music of the spheres can be experienced as a living conversation between physics, melody, and imagery. Implications for science and culture. The idea that celestial motions can be described by harmonious ratios imagines music resonating through the heavens, a metaphor that helps people grasp order in the cosmos. The metaphor ties observed orbital regularity to aesthetic order. In its practice, it invites researchers to seek simple geometric or proportion-based relationships that seem to govern how planets and stars move. Such framing encourages a search for unity across disparate phenomena. For science, the music of the spheres shaped a worldview where mathematics and observation are partners in describing nature, not separate languages. It pushed scientists to express complex motion with elegant relationships. The concept fosters a habit of modeling phenomena as resonance systems, where feedback, harmony, and coherence become criteria for theory. This mindset supports rigorous modeling and predictive thinking. In culture, the idea permeates music, visual arts, and architecture, offering a symbolic framework for how humans relate to the cosmos. Artists drew on the sense of order to shape harmonies and silhouettes. In literature and philosophy, the cosmos as harmonic symphony becomes a metaphor for social balance, ethical aspiration, and the place of humans within a larger design. Religious and cosmological imagery used it to narrate unity between the heavens and daily life. Today, the music of the spheres continues as a productive analogy that spurs interdisciplinary work in mathematical aesthetics, complex systems, and data visualization. It reminds thinkers that data can carry meaning beyond numbers. Yet it remains a metaphor rather than a literal mechanism, and careful distinction is essential to avoid mistaking resonance for causation. The idea endures because it speaks to a shared intuition. Order can emerge from simple relationships and inspire human cultures alike. Tonight, we traced how the cosmos hums with a hidden order. From the early ideas of Pythagoras to Kepler's laws, celestial motions reveal harmonies that endure across the centuries. We highlighted the core points. Orbital relationships can be described by simple ratios. Resonances shape the structure of rings and moon systems, and the metaphor of music helps us feel the cosmos as a coherent whole rather than a random drift. When you lift your gaze at night, you're listening to that ancient score, echoed in the regularity of eclipses, transits, and the subtle dance of distant worlds. If this resonated with you, first I'd love for you to stay connected. Like, subscribe, and share your thoughts in the comments so we can tune the ideas together. In the next videos, we'll dive deeper into the math behind orbital resonances, explore real systems that sing in harmony, like resonant moons and planetary pairs, and even hear how artists translate these patterns into sound and story. Until then, may your curiosity keep its own steady tempo under the stars.